Well, I'd like to welcome you all here to the 2018 Winter Workshop. Actually, we've had 2 days prior to this of the Winter School, and now we are joined by a number of faculty and other folks from around the country. And I want to welcome you all here. My name is Tom Koch, Dean of the College of Optical Sciences. The students have already heard me give a spiel on photonics the other day. And my cold has recovered a little bit, so I hope my voice holds out a little better. I was also asked to give an introduction to the College of Optical Sciences. So in this 20-minute window, I'm going to be trying to do a lot, and that'll mean I'll be racing at light speed. And that's because throughout the day, we will be hearing presentations from a lot of our colleagues at other institutions around the country about their optics programs. And for the benefit of those faculty and others, we didn't have any window like that for our college. So this will be serving double duty. So I'm first going to go through a rapid-fire introduction to the College of Optical Sciences. But first, a welcome to Tucson. I showed this to the students the other day. Tucson is a fantastic place, and I guess those of you from the East Coast and colder climates, we'd like to welcome you here to sunny Tucson. And lots of opportunities to hike if you're going to be around and see animals. These pictures are actually taken from my yard. In fact, these are all these animal pictures are taken from inside my bedroom. So a lot of wildlife, a lot of fun things to see here in Tucson. So please get out when you get a chance to see things. The College of Optical Sciences is part of the University of Arizona, a large state school, and we've got 43,000 students, 18 different colleges across campus. One of the hallmarks of our university is that we're very research intensive. So we have over $600 million of annual research expenditure, and that puts us up in the top couple of universities nationwide in physical sciences research, which has a very specific definition. And a lot of our strong position there is related to our activities in space sciences. But one of the things we do here is get involved in what I'll call big science, and that's fabricating and deploying large systems, and it gives amazing opportunities for our students to participate in projects like that. So here's the university, and here's the College of Optical Sciences along the mall there, and we've got 3 buildings. You're in the newest of those 3, and we're actually eager to look in a couple of years. We anticipate we will have yet another building that we're just a twinkle in our eye right now, but we're moving forward with a shared building to expand yet more activities in optical imaging and technologies. So by the numbers, if you measure by research dollars or by number of students produced, we believe we're the largest optics graduate and undergraduate research program and education program in the U.S. We've got 60 faculty that really call OSC their home. About 35 of those are tenure faculty, 25 or 30 are research faculty. But we also have tentacles into the rest of the university with lots of joint appointments in other disciplines. And it's because it's such a multidisciplinary program. Our faculty are very accomplished. We've had 3 Nobel Prize winners in our faculty. One is an adjunct, is still with us. Unfortunately, Nico Bloombergen passed away earlier this year, but many are in the national academies, and our student body is primarily graduate students. We're about 3/4 graduate students, about 1/4 undergraduates, and we've graduated about 800 PhDs over the years, about 1,400 master's students, and typically we may have about 120 undergraduates enrolled in the college, and that's because they don't start as freshmen. We enroll them from engineering, so we only have sophomore, junior, and senior, about 40 per class, something like that. And the degrees we offer are Bachelor of Science in Optical Sciences and Engineering, a specific master's program in Photonic Communication Engineering. Our most common master's is the Master of Science in Optical Sciences, and of course PhDs, but also graduates' certificates. And we have a distance learning program, which can be a full degree program for many of our students, but also an opportunity just to bone up on specific courses or disciplines that they may want to do. Lots and lots of courses, over 100 courses offered, just about anything you could imagine in the field of optics and so forth. The reason I'm showing this, so this is really for the faculty that are here if they're interested in the economics of education. This shows each of our colleges in the university is a separate business unit, and we get revenues. Most colleges get revenues almost exclusively from tuition, and that's typical of a big state school. But if you look at our college, we're very anomalous, and that's because almost all of our revenue, even though we have a significant student body, disproportionately, a huge amount of our revenue comes in from research. So we are the most research-intensive unit across the whole campus, and that makes us kind of distinctive here at the University of Arizona. So very quickly, I want to race through. This is the part where I'm going to go really fast. I want to cover four of the research group areas, the four research group areas that we organize ourselves into here at the College of Optical Sciences. And the students over the last few days have been exposed to this, kind of organized in these theme areas. These are the way we do it. But I want to talk about each one in particular, so optical engineering, optical physics, image science, and photonics. So if we look just first at optical engineering, that's kind of classical optics, what you would think of, and a lot of optical design. And it's everything from freeform optics to come up with cool heads-up displays to advanced telescopes to imaging systems that might be used for lithography and microelectronics or satellite imagery for remote sensing, things like that. So very sophisticated optical design, really getting a handle on ridding yourself of aberrations and optimizing systems. And the applications that we apply that to are things like astronomy. We're very closely linked to astronomy here, and that includes making the largest telescopes currently in the world, and we actually make them right here on campus. I think the students have had an opportunity to go see those facilities. And what do you use them for? Well, I was stunned personally when I got and understood that people were looking at exoplanets. Most typical way is you look for intensity dips cyclically when you look at a star. But with these monster telescopes, you can train them on a star in our galaxy and actually resolve the planets orbiting the star. So it's pretty darn remarkable that things have gotten so powerful. And that's been enabled by advances in adaptive optics for ground-based telescopes. So this is really cool stuff, and it's getting to the point now where people are going to the next level, train it on one of the planets and trying to do spectroscopy and things like that to see if there's life-supporting chemistry on the planet. We apply it to things like heads-up displays. This is the work of Hong Hua, who's devised technologies that allow you to do 3D imaging, but it's not just stereoscopic. It's actually got depth resolution, meaning if something appears to be deep, your eyes actually have to refocus to look deep. So it doesn't give you the headaches like you'd get when you go see a movie like Avatar, where it's kind of fake 3D. This is real 3D, and it's drawn a lot of interest from the commercial community, especially Silicon Valley, which is into this stuff in a big way now. A lot of work in ophthalmology, things like interocular lenses, new multifocal length lenses for cataract surgery, and things like that. One of the hallmarks, I said, of our university, of our college, is we actually make stuff. We don't just design and engineer it. And we make things, I like to brag that we make optics over 9 orders of magnitude in size. Nobody else in the world can say that. And that goes all the way from 10-meter scale optics, these ridiculously large things, down to fabricating metamaterials and features down on the scale of nanometers. So literally 9 orders of magnitude of size. And if you tour the facilities, you can see some of the tools and hardware we use to do that. Again, really rapid fire. Switching to optical physics. So this is where we do quantum optics, very fundamental physics. Examples here are from Brian Anderson's group, where he works with Bose-Einstein condensates. And this is where you take clouds of rubidium or similar atoms and condense them into a single glob of coherent matter. And the reason I say it's kind of a glob of coherent matter, it's really weird stuff. Macroscopically, you can take 2 of these clouds and kind of nudge them into each other. And this is something you can see in a microscope, macroscopic clouds of matter that start to cancel each other out. It's like taking my arms, and one arm cancels out the other arm. It's real, it happens, and it's even weirder because if you go inside the nucleus of one of those atoms, don't change the chemistry at all, and just add another neutron that would change the net spin of the thing, it wouldn't even work. So, trying to figure out why all that happens and so on, it's very cool physics. Brian is using it to study, and his students are using it to study quantum turbulence. So it's like turbulence in macro systems, but it's quite distinctive because it's really fundamental quantum mechanical stuff. Jason, I think, gave a talk the other day talking about ultra-fast frequency combs, and this is a technology which is really revolutionizing metrology in the time domain, allowing levels of precision in spectroscopy which nobody would have dreamed possible. An example of why this works is if you take a mode-locked laser, its spectrum looks like a series of lines. It's a comb separated by the round-trip frequency. Well, if you pick a frequency there and your pulse is short enough, you can actually get the spectrum to be broader than 2 octaves. Well, why does that matter? If I take one of these frequencies, 2 octaves up, there's this other line right here. But it turns out there's 2 ways to get that frequency. One of them is just because it's part of that comb, extending 2 octaves. But the other one is in nonlinear optics, you can do frequency doubling. So if I double that frequency, it turns out I get this red line, which is almost the same, but it differs by an offset frequency way back at the origin. And so these 2 notes are both present, and they beat with each other, and I can measure that beat frequency, which tells me the offset. That means I know with absolute precision what that optical frequency is. And so this was a revolutionary technique, Nobel Prize winning a bunch of years ago. And it allows people to make super precise clocks where they know things at the level of 10 to the minus 18th. And Jason the other day pointed out one of the amazing aspects of that is you can take an atom and measure its transition frequency and move it from here to here. And you can measure Einstein's gravitational redshift because it got closer to the center of the Earth. I mean, to me, that's mind-boggling. So this is really cool stuff, and Jason's using it to look deep into the vacuum ultraviolet and enabling new spectroscopy in that regime. We also have a group with Jerry Maloney and Miro Kolasek working on ultra-fast, ultra-high-intensity laser propagation. So this is light that's so intense that when it propagates through the atmosphere, it rips the atoms apart and forms a plasma during the pulse propagation, which then recombines as the pulse goes by. So really wild dynamics of atoms and ripping atoms apart as the pulses propagate. And they've come up with fundamental models of how that works. And that's of interest to people trying to do femtosecond pulse remote sensing, but also, of course, the Department of Defense, which wants to blow up missiles and things like that with ultra-short pulses. Okay, I'm not covering everything in each of these areas. I have to go very quickly. Image science is kind of the mathematics of images. So for this group, an image is a vector in some vector space. And it's a mathematical object. And one of the things people would like to determine is how much information is present in that. How do I maximize a system to extract specific information from an image? In other words, what am I trying to find out with that image? I'm usually asking a question, and you can optimize a system to give you that outcome. And sometimes that means the image isn't a pretty image. In the old school, you'd get the best possible image, and then you'd number crunch it. And now people realize that that's not always the most efficient, either from a physical point of view or a cost point of view, to get an answer. So sometimes the question is that a tumor or not a tumor? Other times is that an exoplanet? Not an exoplanet? Is it a good guy or a bad guy? So using the mathematics, people can come up with absolute limits and precision. And that's been applied in areas like gamma ray imaging with nuclear medicine, where a mouse will ingest a chemical with a radioactive species in it that selectively attaches to a cancerous lesion in the mouse, and then you can image where that is using gamma ray emission from the radioactive species. It's not necessarily the goal to extend this to be a big system for people. It's usually used for drug discovery, and the actual species is something small, like a mouse. There's groups, I think you heard yesterday from Jennifer Barton, a lot of work going on in fancy, really enabling endoscope technology, where not only does the endoscope get an optical image, but it allows you to do things like optical coherence tomography, penetrate beneath the surface of the tissue, image things that might be happening there, cancerous lesions growing, even also do spectroscopy, where you can do chemical analysis of what the components of that lesion might be. And these things are now targeting to get so small that they can fit inside something like a fallopian tube, so you don't have to do invasive surgery. So this kind of stuff can be really enabling to get out of the typical paradigm where you have to go in and slice somebody up, do a biopsy, and so forth. You can go in and probe much more non-invasively. The same kind of groups are asking questions. There's a program going on now called Reveal in DARPA, where the question is, what if you look at me and you say, well, what's behind me? You say, well, I can't see behind you. The answer is, well, maybe you can. If you were to look at scattered light coming off the room and you had a powerful enough computer, maybe you could figure out something about what's behind me. And so the question DARPA is asking was, well, all right, what are the fundamental limits of that? And so there's a program going on now to really analyze that. It's obvious why the Department of Defense wants to see behind things, but it applies to other things as well. And the group now is working on this not only kind of in a classical optical sense, but looking at it even from a quantum mechanical sense to really understand the fundamental limits of what's possible. And we've got some new faculty hires in quantum information science, and we're actually hiring 2 more right now to expand that group activity. Photonics is another one of our big activities. The kind of cornerstone of that program was an engineering research center from the National Science Foundation for the Center for Integrated Access Networks. The leader of that is Nasser Pegambarian, and it goes all the way from optical communication network architecture to device and component technologies for switching, generating, routing light, down into fundamental materials and advances for making higher performance stuff, whatever that stuff might be. And we have test beds both at our partner schools in UCSD, for example. This is here at the University of Arizona. And one of the focus areas here was in data centers, because the internet, yeah, there's a lot of stuff undersea going city to city, but a lot of the activity in the internet is actually inside of these ridiculous data centers. So this was looking at technology, especially in that context. We have a lot of work in semiconductor and polymer devices. Bob Norwood has a very vibrant activity in polymer photonics as well as solar energy. And Stanley Powell and others work on microsystems of all kinds, everything from spectrometers on a chip to mass spectrometers on a chip, things like that. So, and that's also enabled by the fabrication facilities we have here on campus. We have fiber draw tower capability and preform fabrication. So that's used to look at specialty fibers in different materials and enable research in things like femtosecond compact mode-locked lasers, where we can make special cool fiber devices. And I think the students got to hear about some of the applications of this technology as well. We are a member in AIM Photonics, the American Institute for Manufacturing Integrated Photonics, and that's a $600 million program based out of SUNY Poly in New York, because they have a $10 billion silicon clean room. But it gives us an opportunity to work with some really remarkable partners, some of whom are here in the audience, and also especially on the corporate side. And we really benefit from direct research programs now with some of these big players in the world of chip scale integrated photonics. For us at the university, at the College of Optical Sciences, industry partnership is a really big deal. It's not just a way to get money. It's most often technology pursued on the private sector. It frankly is at the pinnacle of the field, and it's because companies need to be at the top of their game to be commercially successful. So they are almost always the best in the narrow slice that they're working in, and by partnering with them, we raise our game, and we can contribute also, and because we have a much more diverse perspective on different ways to approach a problem. So we have a lot of activity with private companies. I quote 8 million contracts. That number is changing very quickly. It's going up, up, up. And typically, it's anywhere from 20 to 40% of our research activity is funded by companies. And we really benefit from that. Our students benefit from that, and the companies do as well. We have an industrial affiliates program where we bring those companies twice a year onto campus, and it's not a conference in the sense where we try to gee whiz them with outside speakers and talking about things. It's really an engagement with our students. So the presenters are mostly students, and the companies are there. It's not their HR people. It's their lead engineers or their managers that are trying to find those few PhD or master's students who will make a difference in their company. And just hiring a few of the amazing people can change their world in a big way. So they develop relationships over a period of years and then try to seduce the students into joining their companies. And so it's a real win-win. And it also benefits our undergraduate students as well. And we're developing a new master's program. It's kind of a co-op-like program where the second year of the master's program would be done at a company on site. So very quickly, that's it on the college. I want to just introduce why we're here now, the Winter School and Workshop. First, I want to thank our sponsors. We've benefited from the Dement Foundation, Gretler Foundation, NSF, SPIE, OSA, and the Taxpayer Research Investment Fund here in Arizona. We benefited from a lot of committed leadership here at the College of Optical Sciences, but also outside participation to help guide the direction of this program. This year we've got a lot of institutions, including now we're reaching out also into some of the premier research universities around the country. A lot of wonderful diversity in the students and a good group of outside speakers that you'll hear over the next 2 days. So the Winter School was all about introducing the students to research to get them to understand that optics is more than that. And I hope they've benefited from that. And we had 2 days of talks in the theme areas that I just described and introduced to you very rapidly. So that they ended that over the last 2 days. And now we're embarking on the second portion of this, which is the Winter Workshop. And the objective of that is to look a little bit more into the educational side of things, continue to expose students and faculty to other research opportunities that are going on, but for the faculty here to start sharing some of their experiences and also introduce each other to their programs that they have at their institutions. And this is an eye chart. I know you can't read it, but I think you all have the breakdown here of the 2 days of presentation. So here is today, and we are rapidly approaching 9 o'clock. And we will end the day with a banquet tonight that I hope you all can see, participate in. We also have lab tours, and for those of you who haven't seen the Mirror Lab, it's kind of a one-of-a-kind thing that's fun to see. And then tomorrow we have another full day of presentations and a dinner at a local restaurant with an interesting name, a Culinary Dropout. I'm told it's a great restaurant. I haven't been there myself, but we'll see. So let's launch ourselves into this first day of the Winter Workshop. Actually, I want to mention on Monday, we also have a new ingredient here, which is an immersion day. And this is a smaller number of the students elected to participate in an intensive laboratory session where they're actually not just going in to see a lab, but they're acting as they might if they were a graduate student, actually participating in the research in a half dozen or so labs where the faculty volunteered to sponsor this. So that's an interesting opportunity, and we'll be eager to see how that goes. So thank you, and again, here we are starting the workshop. So my next pleasure and honor is introducing our keynote speaker, and that's Christian Drouet, who is the lead optical engineer of one of our big science programs, which is the OSIRIS-Rex asteroid mission to go out, orbit with an asteroid, land on it. It doesn't have a lot of gravity. Grab a sample off it and bring that sample back to Earth. And in order to do that, we need really good optics to acquire it, to study landing sites, and to study the materials. And Christian was the lead for the camera suite for that project. And Christian received his PhD from the College of Optical Sciences here, and he's worked as an engineer and research and laboratory manager in the astronomy department, the Steward Observatory. And he worked on a number of things, but some of them included technology, especially terahertz technology for imaging applications. And in fact, he joined a company called TeraVision as a VP of engineering, where he helped to develop this technology for radar imaging and spectroscopy. And but then was lured back to have the impact that he's now having with the OSIRIS-Rex mission. So let's welcome Christian. So. And let's see if we can reconnect here seamlessly from from a PC to a Mac. It's the first time it ever worked. That's amazing.
Hi, good morning. So, as I mentioned, I graduated from here, 2003. I went to work at Sirius Observatory for a while, and then my thesis advisor and I started a company, and I got to lead that company for a while. And then about 6 years ago, when the OSIRIS-Rex...
I made a mistake. I didn't transfer
the
mic.
Can you guys hear me before, or do I have to start again?
It's mostly for recording.
Okay.
Well,
all right, anyway.
Why don't you start again for the recording?
Okay. So I graduated from OSC in 2003. I went to work across the street. And then after a few years, my thesis advisor and I from Optical Sciences started a company to build some terahertz radar imagers. The application was for the military, looking for IEDs and things like that. And then the economy sort of tanked, and the OSIRIS-Rex mission was being proposed, and I got to join the proposal team here. And the rest is kind of history, as they say. But so the OSIRIS-Rex is the third mission in NASA's New Frontier program. The first one was New Horizon. I don't know if any of you are familiar with it. It just went past Pluto a couple years ago. It's on its way to another target in the Kuiper Belt. The following one was Juno. It's in orbit right now around Jupiter, taking really interesting measurements. And then the third one is OSIRIS-Rex, which launched last year and is on its way to an asteroid to go grab a sample of it and bring it back to Earth. The fourth mission, NASA just announced they've selected 2 missions that are going to go into studies to come up with the best proposal and kind of fight it out. One is a comet sample mission, so very similar to OSIRIS-Rex, lots of the same people. And the other one is sort of a really extraordinary concept for sort of a helicopter that's going to go land on Titan. All right, so this mission, so that was basically the largest grant the University of Arizona ever got. It was about $800 million at the time, plus another $200 million just for the rocket. There were, during the build, about 700 collaborators that worked on it from 3 different countries, the US, Canada, and France. There's a number more the science team from other countries, but those were the original sort of founding members. We have about 100 science team members, like I said, all over the world. About 60 of them are going to come and live in Tucson in about a year when we're in operation around the asteroid. So they're all going to come here and live here for about a year. And maybe they'll all want to stay, we'll see. So the picture here is from launch. This was September 8th, 2016. It was a very emotional moment. It was a beautiful launch. And recently, in September, the spacecraft went by Earth for an Earth gravity assist. So we basically used the gravity of the Earth to get a little more momentum on our way to the asteroid, to get outside of the plane of the ecliptic and catch up to the asteroid with less energy. We're planning on getting to Bennu, the asteroid where we're going to, next summer. And we're going to be there for a couple years. Hopefully we get a sample at the end of those 2 years, and then we come back to Earth in 2023. So if you look from the beginning of when we started playing this mission, 6, 7 years ago, to 2023, this is kind of the time life of this mission. It's pretty long. So there's an interesting connection to the College of Optical Sciences. The college here was responsible for one of the 3 instruments, the 3 cameras that are on the OSIRIS-Rex spacecraft. The Polycam, it's a 8-inch, 20-centimeter reach gradient telescope. It's kind of a 2-mirror telescope. So it was designed and built here, very close to here in the basement over there. And then the College of Optical Sciences also helped with the design and of the MapCam and the SAMCam. So in all, 22 optical science, College of Optical Science graduate contributed to the project. And you can see in here a lot of PhDs, but a number of students were involved. And I think that's pretty remarkable, for students in any programs to actually get to be, involved directly with building space hardware, not just some peripheral involvement, but actually building things and helping with the design of space hardware. And so I was lucky to have a couple PhD students that worked for me at the time. We also had a couple undergrads, and they're all working in the optical industry now in and around Tucson. So just a little bit more about what OSIRIS-Rex is and what the acronym stands for. So it's a NASA project, so it has to have an acronym. The longer, the more complicated, the better. If you can have an acronym within an acronym, you're doing even better. But basically, OSIRIS-Rex stands for Origin, Spectral Interpretation, Resource Identification, Security, and Regolith Explorer. So the idea is the origin part is we're going to go to an asteroid, something that has never been explored before, and we're going to grab a sample, and we're going to bring it back. And that's going to tell us something about the origins of our solar system. The spectral interpretation part is basically relates to we can look at a lot of asteroids from Earth and look at their spectra and just their color and various other things. And from that, we can infer some of their properties, what they might be made of. But we need some ground truth to really make sure that we understand what's going on. So by comparing what we see of this asteroid that we're going to visit now and what we imagine is going to be like and compare it to what it really is when we get there, we'll be able to help us improve how we understand something that we haven't been to before. The resource identification part of this is there's a number of asteroids out there, and when we look at their spectra, we think, oh, there's probably water there, or there's some valuable metals. And being able to understand what's there can guide us to direct other missions to go get water in space for other projects or get some metals that are very hard to mine on Earth or something like that. The security part of this is that some of those asteroids every once in a while will collide with Earth. And most of the time they're very, very small, so you see a shooting star, or they're a little bit bigger and you get a bolide or something that's very pretty. And every few million years something hits that does a lot of damage. Like 65 million years ago, a big one hit Earth and killed all the dinosaurs. And we don't want that to happen. And the last part, the Regolith Explorer, I kind of joke about this part because OSIRIS-Rex was proposed in one version or another 3 times before it was funded and selected by NASA to fly. And NASA has a rule that you can't propose the same thing with the same name multiple times, right? You have to have at least a different name. And so OSIRIS got recycled. That was OSIRIS-Rex, and that's when it finally got funded. So the Regolith Explorer is basically, well, we took the same mission. We changed this cost cap. We changed the pricing and everything to make it better, and also change the name a little bit to say we're going to explore the regolith, which is true, but it's not really that key. So asteroids. I don't know. I mean, I think most of you are probably from a physics or engineering background, so I don't have to tell you too much about asteroids, but they're basically little rocks that are in general orbiting between Mars and Jupiter. Some of them come all the way inside the orbit of Venus, some of them go way beyond Jupiter, but the vast majority of them are between Mars and Jupiter. And they're sort of building blocks of the solar system that never quite coalesced into a planet. And every once in a while their interaction with Jupiter or some of the larger planets just kicks them in on the inside of the solar system, and that's when from a security standpoint, they can become dangerous because as they start migrating into the inside of the solar system, well, some of them will come into contact with Earth. When I started becoming interested in astronomy, asteroids were kind of the, they were not considered very interesting. They were sort of, what was left of the formation of the solar system, and nobody really cared about them. Some people even call them the vermin of the solar system. But starting 30, 40 years ago, some of the pioneers, including Mike Drake, who led the mission, the OSIRIS-Rex mission originally from the University of Arizona, started realizing that when we look at meteorites, those meteorites are actually chunks of asteroids. And when we look at what those meteorites look like, we can actually start relating something we have in our hand to something we observe in space. And so all of a sudden we can actually do chemistry and all sorts of things on objects that we can relate to something that's in space. So we spent a huge amount of money and resources going to the moon to get a few samples, but all of a sudden we have all these samples from space that just come to us for free. And so that kind of gave a new birth to the field of asteroid research, because once we started realizing that we had all these samples, it was very valuable. The other problem with asteroids, one of the reasons why they weren't very exciting originally, is they tend to be pretty small, and they're far out there. So when you look at them, you don't see a whole lot, right? And if you take your best telescope, this is a picture of one of the larger asteroids from the Hubble Space Telescope, and yeah, well, it's kind of an interesting picture about what's going on, right? I mean, you don't really know. All you can tell is it doesn't look quite round, and there's some things going on. So when you send a spacecraft up close, it doesn't have to have a huge telescope on it, but just by virtue of being close, now you can start seeing that, yeah, this asteroid that looked a little funny with our best telescopes from Earth, really something happened. And in this case, it's this huge impact crater, just about the size of the asteroid itself. And the interesting thing about this is that explains why when we're on Earth and we're looking at some of those rocks, we see a lot of these chunks that appear to have come from an asteroid with similar photometry, similar color as this, because there was a major accident where two asteroids hit each other. A big chunk of this was just kicked out into space, and then year after year the Earth went through the solar system and harvested a lot of the chunks. And so we can actually now say, oh, these rocks that fell on Earth came from this asteroid, and we can relate those families and try to understand a little bit more. The other interesting thing about going there is, these things that just look like little dots, once we get there, they have those crazy shapes, right? And it's kind of, now you have to sort of wonder, well, how does something that looks like a banana form out there in the solar system? I mean, what's the physics behind it? And the more we explore objects, the more we find things that don't look at all like, what we would expect from a body that just formed by accretion in the solar system. Now this is a little chart that shows all the places we've been, and if you look, most of them look pretty unique. I mean, there's no two that are like, the really large ones, gravity starts to pull them into something that looks like a sphere, but all the small ones, they have these unique shapes from how they were formed, how the material accreted, and so it makes it pretty exciting to go to some place that, we don't really know. So now this is a quick video that shows how, at what rate asteroids were being discovered. So at the turn of the century, there were a few hundred asteroids that were known. And then, by the 80s, there's something like 11,000. On this, what you see in the center in yellow is the Sun. Orbiting right around it is Mercury, then Venus, then Earth, then Mars. And then every once in a while, you will see Jupiter come all through the corners, maybe on the lower side in a minute. Now, can we turn the lights off? Is that all right? Because you can't really see very much. But the white dots is basically any time an asteroid is being discovered, you can see a white dot appear. And then it starts to fade out and turns green if it's in the belt between Mars and Jupiter, and turns red if it's in an orbit where it can potentially come into contact with Earth. So there's a few things that are remarkable about how those asteroids are discovered. You can see that they're typically discovered at what we call opposition in astronomy, meaning that if this is the Sun, this is Earth, the asteroids are being discovered at night, right? Not too crazy. It sort of makes sense. Whenever you're at night and you're looking away from the Sun, that's where you're going to discover asteroids, right? The other thing you can start noticing after a while is there's sort of this, there's Jupiter here in the corner to give you a sense of scale. You can see sort of this pulsation where we discover a whole bunch of asteroids and we don't discover a bunch of asteroids, and then again and then not. And this pulsation corresponds to the cycle of the moon. Right? When the full moon's out there, you're not going to find as many asteroids because the background of the sky is much higher, right? And you tend to not even go look. But so basically this pulsation that you're seeing is every time the full moon versus new moon. Another thing that's interesting about asteroids being discovered is by the time you get to the 2000s, the rate at which we're discovering asteroids is just grown incredibly, and that's all because we got electronic sensors versus film sensors and dedicated surveys with computers looking for asteroids. Something that's interesting, if you look out here in this region, somehow there's always not a lot of asteroids being discovered there. And so this region, that corresponds to a part of the year that's roughly July to August. And that's the monsoon in Arizona. So 60 or 70% of those asteroids are being discovered in Arizona and New Mexico. And when it rains here, well, you can't open the telescope and you don't find asteroids. So anyway, we're almost back to today, and by now we know about 500,000 asteroids out there. So again, the green ones are the ones that are safely between Mars and Jupiter. The red ones are the ones that come to in orbit close to Earth. So kind of going to the point of a lot of the asteroids being discovered here. So 52% of all asteroids were discovered by U of A. A lot of them by the Sky Survey. A lot of them by Space Watch. And then even those others are typically in Arizona as well. So just real quick on the security aspect of why do we want to go to asteroids, why do we want to understand what they're made of and how they travel. Just here in Arizona, we have a large crater. If you ever get to go, it's kind of a fun place to visit. It's by Flagstaff. It's about 7-hour drive from here. But anyway, you can see what happens when a 50-meter asteroid impacts Earth. That's 50 meters, right? The asteroid we're going to go visit is about 500 meters. So, the other thing is, we know those happen every few thousand years, and it's like, well, what's the big deal? But if you look at actually what happens on Earth every day we get about 100 tons of asteroids hitting Earth. They just happen to be very, very small, so we don't feel it. But even the bigger ones, this is a chart that shows from, sort of a 20-year period, pretty major hits. And those are not things that left craters or kill people, but those were left sizable chunk on Earth. So it's not something that's that rare. And then of course there's what happened in Mexico that killed all the dinosaurs 65 million years ago. And this is one of my favorite justifications for why we should have a space program. All right, so all these asteroids out there, we want to know where they're going, right? Because if one of them is going to hit Earth, we're going to want to know, we want to be able to do something. That means we have to understand where they're going. And so when I went to college, we talked about physics, and everything was perfectly constrained, and in theory you could figure out where anybody in the solar system was going to go at any time and project it as far in the future as your computer would allow you, right? And astronomers have gotten very, very good at this, the whole gravity aspect of what's happening in the solar system, looking at the right bodies and which one matters, and they have gotten very, very precise. However, there's actually an optics component to what happens to those asteroids. So as a body is traveling in the solar system, especially a small one, the side that is facing the sun is getting hot. And as the asteroid is spinning, that hot side is turning. And at some point it will be facing away from the sun, but it's still hot, and it's radiating infrared radiation. And that radiation carries momentum. And it actually can slow or accelerate the asteroid on its trajectory. And so you have a physical effect due to radiation from the sun just heating up the asteroid and causing the asteroid to speed up or slow down. And that prevents you from using just gravity and figure out where an asteroid is going to be in a few years. That doesn't seem like a huge effect, but it turns out if you look at Bennu, the asteroid that we're going to go visit, from the time it was discovered to 12 years later when we reobserved it in a path close to Earth, its trajectory had changed by 160 kilometers. So this is a half-kilometer asteroid, and over a space of 12 years, if you just use gravity, you would have been wrong by 160 kilometers. Well, that doesn't sound like a lot, but you do 160 kilometers over a period of a few hundred years, and all of a sudden, you're predicting it in completely the wrong place. This asteroid Bennu that we want to go to is one of the ones that has the highest likelihood of impacting Earth. It's a very small likelihood. It's 1 part in 2,000, something like that, in about 100 years. And what determines whether it will hit or it will miss is about 10 years or 12 years before the potentially dangerous pass, is the asteroid will go between the Earth and the Moon. Right? And there's sort of this keyhole that it has to go to in order to hit Earth 12 years later. If it goes on the Earth side, then it's going to get diverted one way. If it goes on the Moon side, it's going to get diverted the other. If it goes right through the keyhole, 12 years later, when it comes back, it's going to hit Earth. And that keyhole is only about 1,000 kilometers wide. And so if you're off by a few hundred kilometers, it matters a lot, right? It's the whole difference between missing completely or hitting. And deciding, oh, we should go nudge it, try and get it out of the way so we don't get hit, and just pushing it just enough to make it go through the keyhole. So it's really important to understand what's going on with this Yarkovsky effect, which is what this acceleration of asteroid is called. Now, the other thing about this effect is, depending on the albedo, the amount of energy the asteroid absorbs, the solar energy the asteroid absorbs, some places on the asteroid might be brighter, some places might be darker, some places may radiate quicker because of what the asteroid is made of, and those local differences will cause the asteroid to spin up faster or spin slower. So in addition to this effect that's accelerating the asteroid based on its rotation, light is also changing the rate of rotation. And so you have all these effects that are caused by optics, by just the absorption and emission of photons that are changing the way the asteroid is behaving. And so part of what we want to do when we go to Bennu is really understand how all these physical processes work, so that in the future we can apply it to other asteroids that we discover and decide whether, well, this is going to be in a place where it's dangerous or no, it's not. So when we were choosing where to go for this mission, we started by looking at about this 500,000 known asteroids, and then we picked that sample and we downsized it to about 7,000 of them, which are the 7,000 asteroids that are known to come close to Earth, that are potentially dangerous, right? Out of this 7,000, we were able to narrow it down further to 192 that had orbits that are such that we actually can, with existing rocket technology, go to one, get in orbit, get a sample, and come back. Because we have those big rockets that allow things to go like New Horizons, to go all the way to Pluto really, really, really fast. But it's one thing to just accelerate, but if you have to accelerate to go to something, and then you have this body that has no gravity, now you have to brake to get there. And then you have to accelerate to come back Earth. And then you got to slow down so you don't burn up in re-entry. You have all these steps that require a lot of rocket power. So even though we can send a spacecraft all the way to Pluto, we can't just send a spacecraft to any asteroid and come back to Earth. We have to pick ones that are fairly advantageous from an energy standpoint. So that got it a little bit down for us. Then the next thing was we looked at which ones were bigger than 200 meters. The reason for that is the asteroids that we know that are smaller than a couple hundred meters, they tend to spin so fast that trying to land on one, we would never be able to land on one. Because if you're trying to land on something that's spinning, once every couple of minutes, and you're trying to, match its rotation, you're going to just get hit by something, right? So we picked one of the larger ones so that it would rotate slowly enough that we could match its rotation and land on it. Then the next step of narrowing this down was to look at carbonaceous asteroids. So I told you part of what we know about asteroids is by looking at meteorites. So there's a number of different kinds of meteorites that we find on Earth. A lot of them are iron-type meteorites. rock-type meteorites. And then we know there's also things that have carbon in them because we can see them in space, but we don't see that many of them. And the reason is when an asteroid or a chunk of an asteroid goes through the atmosphere, if it's made out of iron, usually it makes it all the way to the ground. If it's made out of rock, it may come down a little charred, but it still makes it down to the ground. If it's a piece of coal, well, most of the time it will just burn up in the atmosphere. Right? And so we don't really get any of those. And so in order to sort of get the maximum science benefit from going to an asteroid, we decided to go to one that we don't get very many of, because when they come to us on their own, they burn up in the atmosphere. We don't really get to see what they're made of. And then finally, out of those, we picked one that was discovered fairly recently before. It was just sort of the best candidate of all this. So to give you an idea of the size of what we're going to, this is the pyramids in Egypt. So it's pretty big, but it's not that big, right? It rotates in about 4 hours, so every 4 hours. And it's suspected that it's not actually a cohesive body, but it's actually what they call a rubble pile. It's just an aggregate of rocks that are pretty loosely bound. I mean, the gravity at the surface of this asteroid is just incredibly low, right? I mean, we're talking about millionth of what it is on Earth. And one of the interesting things is, if you're familiar with the escape velocity, right? So let's say you have a Earth and you want to launch a rocket, you've got to accelerate to something like 11 kilometers per second, right? And at that velocity, you're basically going to escape the velocity of Earth. On Bennu, if you have a rock on a hill at the top of Bennu, and it starts rolling down the hill, by the time it rolls down to the equator, it's going fast enough to escape Bennu. Right? So this is kind of the world we're talking about. This is just kind of crazy gravity, right? When we're the whole spacecraft, which weighs a couple ton, the gravity that the spacecraft is going to feel from Bennu when it's touching the surface is going to be about the same amount of force as 2 or 3 grapes on Earth. So if you take a couple grapes and you feel how much they weigh, that's the tug that the spacecraft is going to experience when it's at Bennu. So when we get in orbit at Bennu, we won't be just orbiting the body, but the orbit is actually calculated to be behind the body, so that you have the solar pressure, so the solar pressure from the light and everything coming from the sun, and then we're going to be just balanced by the gravity. So the gravity of the body is able to just balance the amount of pressure from the sun. So if you're out there in the solar system and you're feeling, photons and particles from the sun hitting you, well, we're going to be a couple kilometers away from Bennu, and the gravity from it is just going to be just enough to balance the solar pressure. So we were lucky because after it was discovered, this is one of the reasons why it was selected, I think, we were able to get a lot of resources to go try and understand as much as we could about Bennu. And one of the opportunities that we had was a couple years ago. It went close enough that we could use radar to image it. And so this is, to the best of our knowledge, what the surface of Bennu is going to look like. Now, everybody on the team just wants to know whether this is true or not, because honestly, no one knows, right? But this is our best guess as to what this thing looks like. And so in about 6 months, when we get there, or maybe 8 months when we start getting pictures, the big question is going to be, does it look like this at all, or is the radar just completely full of it? All right, so this is just kind of shows sort of the schedule of the project. Like I said, we started in about 2011. Launch was in 2016. We just went by Earth gravity assist, and then later this year is when we start getting close. And then we're going to get into orbit, do a lot of observations, and then hopefully try and sample. I have a little video to so this shows the OSIRIS-Rex spacecraft. It's about the size of an SUV or something like that. So you can kind of get a sense of how big it is compared to the body. This is flying pretty close to it, so it's, This shows we're not actually using laser or anything like that, but it's just illustrating the fact that we're using our cameras, different spectrometers, to get a sense of what Bennu looks like up close, what it's made up. Then when we've decided on a good place to go sample from a safety standpoint and from a scientific interest standpoint, there's this long arm that deploys and has a canister that looks like an old cell carburetor filter that's about this big, gets deployed at the end of an arm, and then the whole spacecraft is brought down. And it's not an actual landing. We call it a touch and go, because what we're doing is actually bouncing off the surface of Bennu. Now the Europeans went to Comet 67P, one of the images I showed, and they tried to put a lander, and on the first time it touched, it bounced. It bounced several kilometers high and landed several hours later somewhere else, right? So one of the things we're trying to do is to not land, is to basically have this controlled descent, hit, and then bounce off, right? And then this shows that, once we got a sample, we put it in the sample capsule, we come all the way back to Earth and get the sample capsule back to Earth. So the ultimate goal is to get some of these rocks that have never experienced any human contact all the way home here, where we can do all kinds of analysis. And one of the neat things about this is we're not going to analyze all of it right away. I mean, about half of it or more is going to be saved for future generation, future technology, because there's, if you look even just 50 years ago, the kind of technology that was available in chemistry and kind of things that we were able to do, there's so much more that we're able to do now. So a lot of it is just going to be banked for the future. I mean, obviously we're not going to look at we're not going to not look at things, but at the same time we're going to save a fair amount of that sample for the future. All right, so it takes a lot of systems and a lot of optics to get a spacecraft like this to work and do its job. So the key part, obviously, for this mission is the sampler arm, the return capsule, but everything else is there to help service that. So what we have is in terms of optical components, there's star trackers. There's 2 star trackers that allow you at any time to know how the spacecraft is pointed in space. So it takes images of stars, star fields, and it's able to tell based on which stars it's looking at and what clocking they're at, how the spacecraft is pointed. There's also laser rangers that allow you to know, once you're in close proximity to the asteroid, how high you are. It's kind of similar to what you have on an airplane and you're getting ready to land, and there's a system that basically tells the pilot how high they are. We have, obviously, the systems that we built here. There's 3 cameras. There's what we call the Polycam, the MapCam, and the SamCam. The Polycam is a pretty sizable telescope. It's 8 inches and allows you to detect the asteroid from a couple million kilometers out and helps you navigate all the way close to it. Then once you get close to it, we can use the MapCam, the mapping camera, to create maps of the whole asteroid at a resolution of a half a meter scale or something like this, or maybe even better, 10 centimeter scale, in color. And using different filters, you can use those color images to tell you something about what kind of minerals are present there. And we also have the sampling camera, which is kind of a video camera to document the actual sampling event. So we know where we actually got this sample from, because it's good to get a sample home, but from a scientific standpoint, you really want to know where you got it from, right? And not just that, oh, well, we were aiming for this general region of the asteroid, but you want to know that, everything went the way you were planning, and this is the location where you got it from. We also have 2 spectrometers on board. There's one that's a visible through mid-IR spectrometer. It's called OSIRIS. And then we also have a mid-IR to long-wave IR called OTES that was built at ASU. And then there's a student experiment that was built by Harvard and MIT students. So this was a non-critical instrument, but it had a pretty sizable budget. And basically, from start to finish, it was students at those 2 institutions that got together to build this X-ray spectrometer. It's an X-ray imaging spectrometer. And the official requirement of this instrument was to learn, for the students to learn about, aerospace. So it was kind of something where either way it was going to happen. But the amazing thing is they actually managed to deliver a working instrument that's going to deliver real science at the asteroid. So this is a group of students, some of them undergrad, some of them grad students, completely student-led with a couple advisors to try and help them go down the path. All right, so now we have this. I hope the video plays. It takes a little while to get started, I think. Okay. This shows you a simulated sample event. Obviously, we want to know if this idea will work, right? And we have this crazy idea. We're going to go to some place. We're going to touch it for a few seconds, and then we're going to get a sample. So what they've done is this is Lockheed Martin in Denver who came up with this sampling mechanism idea. And what they've done is they've done it under vacuum, and then they've done it with all kinds of different rocks. And then as we got closer and closer to the finished idea, we actually took this on an airplane under zero gravity. And so you have this sample using rocks that are very similar to rocks that I've found on the moon and other planets. And then doing those parabolic flights, getting to 0G or close to 0G in vacuum, basically exercising this system. And this has been done hundreds and hundreds of times under different conditions to try and see and guarantee that we will get something. So that we understand also when we pick a place to go sample that, if there's boulders that are more than this size, more than a few centimeters, or if there's no boulders that are less than, half a centimeter or something, then you're not going to get such a good result. If you guys have any questions while I'm talking, feel free to stop me. Anyway, so this is also a cool little video. This is one of those, if you ever had in physics one of those air tables where you could try little experiments with no friction. They built this giant one, put a fake spacecraft on it, and then basically extended the arm and then threw it at about the right speed at a piece of board, and then watched and made sure that everything, all the timing would be about right. But part of the reason why I wanted to show this is this gives you an idea of the speed at which this happens. So the spacecraft is now in free fall from 100 meters or something like this, all the way down to the surface of the asteroid. And this is the speed at which it's going, which goes back to the kind of gravity we're talking about. We're talking about the same amount of force as the force from a couple grapes falling. All right, so then this shows why we were building the spacecraft at Lockheed with the arm extended. It kind of gives you an idea of size. Something that's interesting is the arm and a lot of those mechanisms are designed to work in space where there's no gravity. And so they don't work so good on Earth. And so, for example, when this was being tested, the arm is actually hanging from a giant helium balloon that's inflated in this really, really tall building. And so you can see at the top, there's this big helium balloon that's tugging on the arm to try and compensate its weight so that the motor are able to do their job without overheating. And this show a rehearsal. I mean, obviously you don't want to get all the way to an asteroid, get a sample, you have it in the sample holder, and then you try and put it in a capsule and it doesn't fit. Well, that would not be good, right? So every one of those steps are rehearsed as the thing is being assembled. And so this basically shows one of those operations where the arm is being folded to go back in the... Okay. So since this is about optics anyway, I wanted to have a little summary here about the different instruments that we have and where they fit on the electromagnetic spectrum. So starting with REXIS, which is this MIT Harvard student instrument that works in the X-ray, looks at fluorescence. So basically what it's looking at is X-rays from the sun hitting the asteroid and then fluorescing at some lower energy that is going to depend on what the materials are at the asteroid. Then we have OVIRS and OTES, the two spectrometers, visible through IR, so visible through 4.5 micron, and then OTES 5 microns out to about 50 or 60. And then the R cameras, OCAMs, that basically span the whole visible range. There's also a Canadian instrument, the OLA, the OSIRIS-Rex laser altimeter. That's a scanning LiDAR. So a LiDAR is just like a radar that's used in for tracking aircrafts or whatever, but it actually uses a laser. It sends a laser pulse and times how long it takes for that laser pulse to come back to tell you how far away you're from an object. And if you have a scanning LiDAR, what you're able to do is basically take a 3D picture of what you're looking at. So for every pixel in the image, you actually, instead of getting a return intensity, you get a distance. So you can make those maps of surface heights, which obviously is very helpful if you're trying to plan on landing somewhere and you want to make sure that there's not going to be a big boulder or something that you're going to run into on the way. You want to have not just a color map, but you also want to have a surface map. All right, so this is what the instruments that we built here look like. SAMCAM, the MapCam, PolyCam. I mentioned before that the PolyCam that was built here at Optical Sciences, it's used from the beginning from a couple million kilometers away, but it's also used from all the way down to a couple 100 meters away. And from a couple 100 meters, the resolution from the PolyCam is sub-centimeter. So we're going to have this body in the solar system, and we will have maps of the regions where we're planning to go get a sample that are going to be precise to sub-centimeter. I mean, we don't even have that for Earth, right? I mean, we don't. You can't go to Google Maps and get a picture that shows you the surface of Earth with a resolution of half a centimeter. That's just, can't get that. Half a meter if you're lucky. So that's one of the things that's exciting about the PolyCam is it's a really powerful telescope, and it's refocusable all the way down to a few hundred meters. And so we're going to be able to have those recon passes when we get images that tell us, this is the site where you want to go get dirt from, and you will be able to tell, is there material on a size scale that you're going to be able to sample? Are there rocks that are more than 2 or 3 centimeters there that are going to be a problem and try and get in the way of your sampling? So that's one of the powers of this PolyCam that was built here. The MapCam, the nice thing about the MapCam is sort of a telephoto lens, and it has all those color filters that allow us to look at specific types of rocks. So specific types of rocks will have little spectral features, and by looking from the difference from one filter to another, we'll be able to tell whether some of those rocks may have been hydrated in the past, whether those are regions of the asteroid that perhaps have more water than others. That's one of the things that's exciting about asteroids is there's the possibility that all water on Earth may have come from asteroids. So there's a big debate in science whether it's comets or asteroids, and then based on isotopic ratios, you can probably tell. So those are just pictures from when the cameras were developed, the spectrometers, OVIRS at Goddard Space Flight Center, OTES at ASU, and then Rexus at MIT. Okay, so I have a few more minutes. So OVIRS is kind of an interesting, it's a very simple, in theory, a very simple instrument. Basically, it's just 2 off-axis mirrors. They get the light from the asteroid, and they focus it on the detector. The detector has some filters of different colors, kind of a Ray-Ban, not Ray-Ban, what's the name of that company? This company that made sunglasses that had different colors. I forget the name. Oakley, right. So Oakley started this, and basically it's the Oakley detector is what I call it. So on the detector, and it's made, and the filters are made by Oakley, so I'm only half joking here. It's the same factory. And so basically, you get light on there, and then depending on which pixel you're looking at, you're sensitive to a different wavelength. It's a very solid instrument. One of the things about it is, of course, it needs to be very well thermally controlled, right? Because you don't want light to end up in different places and efficiencies to be different. And so it's all built out of this. So the whole thing is built out of this aluminum case. The mirrors are aluminum. Everything is matched. All the materials are matched so that the focus doesn't change as it gets hot or cold, because it's an instrument that needs to work at cold temperature in order to be sensitive in the infrared. And so they have this beautiful thing, which of course, aluminum, for standpoint of reflecting light around the box, is not ideal. So then you have to put some sort of a black coating, a very special black coating that absorbs not just the UV, but the visible, the infrared, there's only a few places that can do that. So you have this very nice machine structure, and you send it to get this black coating. And then bad things happen. Factories burn down sometimes. And then your precious box, well, doesn't always make it. It's very black, yeah. So the OSIRIS team, they basically had to go find a prototype in a hurry, and then refurbish it, and then wait for the factory to come back online. But in the end, they did manage to pull it through. But it's one of those things where you start one of those big projects, and I remember a NASA QA guy coming to us here when we were starting and asking us about our fire protection plan. And I was just like, fire protection plan? And then about a year later, this happens, right? And so it's, those big projects, things do happen, and it's kind of crazy. So this is OTES, and so it's a nice Michelson Fourier transform spectrometer. And among the things that it has that are pretty cool is they replaced what for a long time they've had those infrared window material, and they're very fragile, they're very hygroscopic. Over time they can degrade. If the spacecraft sits a long time at Cape Canaveral where it's very humid, bad things can happen. So they were able to replace it with CVD-grown diamond crystal. So they have a 2-inch diamond crystal in there as their beam splitter, which I think is, it's amazing how some technologies that are developed for the rest of the optical world still manage to find their way and make our instruments better. But it's a Michelson interferometer, which are very sensitive to vibration, right? And it doesn't have any fancy isolated optical table or anything like that. And so when it got integrated to the spacecraft, it got put on a purge line. Like all the instruments, to try and keep them clean, we try and keep extra pressure inside of the instrument so dust can come in. But all of a sudden, they started getting bad data, and they just struggled to understand what was going on. And they were ready to ship the instrument home when somebody just realized, wait, let's disconnect the purge line and see what happens. And sure enough, everything got quiet and beautiful again. Because when you're on a spacecraft in space, it's not a lot of vibration. You don't have to have a vibration isolation table. But if you're on a spacecraft on Earth and there's big fans and there's purge lines that are sending air and moving microphonics and moving things, then all of a sudden you get into real interesting things. I think just for time, I'm going to skip a couple of those and talk a little bit more about our project. So the 3 instruments that we built here was a core people of about 45 people with roughly 50 contractors that were hired. So 45 U of A staff, both from optical sciences, from Stewart Observatory, from LPL, and then about 50 contractors that were hired either from other companies or just brought in for the project. And the project went on for about 4 years. We built 3 cameras and then a computer controller that talked to all those cameras and talked to the spacecraft. What this shows is the 3 cameras, they work pretty much from infinity all the way down to 100 meters for Polycam, 30 meters for Mapcam, and then just a couple of meters for Samcam. And then that gives you an idea of the resolution that we can achieve with those cameras during various phases of the mission. And so we are going to get a lot of images of the surface of Bennu at sub-centimeter resolution, probably some of them around millimeter type resolution from when we're really up close to the surface. So this is a picture of Samcam, which Samcam was always our baby. So it's only about this big. And Samcam never had any problems of any kind. It was just the camera that just everything went right. So I'm not going to talk about her because, Now Mapcam is a Mapcam camera. So again, it's sort of a telephoto lens type camera. Has filters. Kind of hard to see here actually. There's a filter wheel here. All the filters are in here, and then the detector is there. One of the things that's interesting is when you're designing cameras for space, you have to use radiation hard glass, and there's not that many of them. And so you're not able to do as good a job of achromatizing the system or compensating for all the aberrations to get really nice images as you would if you were able to borrow from the whole library of glass you can buy for making optical systems on Earth. So one of the ways we went around this was we used filters of slightly different thickness to compensate for the chromatic aberration. So the blue filter had a different thickness than the red filter had a different thickness than the green filter, so that in all cases we ended up being in focus. Of course, that makes it for a complete nightmare in terms of managing all those different filters and where they go and everything. And this was one of our horror stories where we picked this one vendor because, well, it's a government procurement and they were the cheapest. And they initially did some pretty good job, and then Tropical Storm Sandy happened, and they were never able to recover. So they had done some beautiful prototypes, and then after the storm flooded their workshop, they just weren't able to come back ever. And so we basically had to ditch them and go with we had to survey all the vendors again and then pick one that was more expensive but hopefully would deliver. They did a beautiful job, and then they were in Boulder, Colorado, and this was the summer when Boulder had the floods. And so they had our parts, and we thought they were okay, but nobody could get to the factory for about a week. And in the end, everything was fine, but it was just, again, one of those things where, you start the project thinking, oh, really, what are the odds, right? Tropical storm? Floods in Boulder? When does that happen? And it ends up impacting you, which is it's both fun and at the same time just mind-boggling that, but if you have a project that has things going on for 5 years and you have so many activities going all around the country, chances are you're going to be affected. All right, so this is Polycam. Basically shows the design. It was a pretty simple Ritchie-Chrétien design. One of the things I can say about this, for example, is all of the stray light control structures. So all of these bafflings, all of this was completely done by a student, an optical sciences student. This was his entire responsibility. No one else worked on it. We just got to, basically make sure that what he was doing worked. But this is kind of this type of task that a student here was able to do on, a $1 billion type space project. So I think it's, it was pretty impressive on the resume. I can tell you did not have trouble finding a job. All right, so this is just the pictures of our babies when we got them finished. A big part of those space cameras is not just designing and building them, but it's testing them and understanding how they work, right? And so this is one of the strengths on the U of A side is we were able to do all kinds of radiometric calibration and test some of the stray light. We were able to do thermal vacuum testing, and then a number of tests. But there's also a number of areas where we don't have all the capabilities because we're a university. Even though we're a big university, we don't have all the capabilities. Fortunately, we have friends at SDL. Jed will talk later. And we were able to put all of their facilities to use. They have an amazing stray light testing facility that we used for the Polycam. It's shown here. It's basically a black hole. You walk in there, and there's no light. You have no idea where you are. It's complete isolation. And if you're standing where the camera, it's even worse. There's no reflection from anywhere. And then we also used their vibration table and a lot of their electronics production facility. That was just, it was a really good complementary teaming arrangement that just came about and is being reused for other projects. So then once we've built all those 3 cameras that do their own thing, then we have to put them all together, make sure they talk together, they don't interfere with each other. Not only do we want them to not interfere with each other, but we don't want them to interfere with the spacecraft. So we take them to a place here in Gilbert Orbital, and they have this big anechoic chamber where they can essentially listen to the electronic noise that's coming out of your cameras so that you can turn them on when you go on the airplane. or on a spacecraft in that case. But then also the other way around, we want to be able to throw a whole lot of interference at them and make sure they still work, because there's other things that are going on in the spacecraft. The spacecraft might be talking to Earth at the same time, might have a traveling wave tube amplifier going on at the same time, might be some other instrument. So really you have to test both that you're not interfering with anything and also that nothing is interfering with you. And then we shipped to Lockheed, FedEx white glove service, and integrated on the spacecraft. And once we were integrated, we got to actually test it, make sure all the optics were still working. That was kind of fun, basically walking from the spacecraft and taking images of the team using the cameras that were going to fly in space, and verifying that, for example, the SAM-CAM was able to see what it needed to see. So this is basically an image taken by the SAM-CAM, the sample camera, of the sampling mechanism, right? And these are about 5 millimeters across, so the resolution is about 1 millimeter. So what we can expect to see at the time when we're actually sampling is we expect to see things down to about 1 millimeter of the surface of the asteroid. And then, you've spent all this time testing your camera on its own, that it resists going hot and cold, resists going to vacuum, resists vibration. Well, once it's on a spacecraft, the whole thing goes on again, where the whole thing as a team has to work and go through all this. And so the whole spacecraft goes on to vibration, goes on to electromagnetic interference and compatibility testing, and then also goes on into this giant thermal vacuum chamber, where the whole spacecraft gets lowered into this big vacuum chamber. Vacuum gets pulled. They have some huge flood lamps simulating the sun to heat it from one side and vacuum or from another. And this just kind of shows how it's being done. And this is something that, runs for days and nights and doesn't stop for weeks at a time. And then the whole time this is going on, you're all in the control room pretending you're operating the spacecraft in space. So it's kind of your first taste of having the team 24 hours a day running the spacecraft and making sure everything is working correctly. Then we ship to the Cape, unpack everything, do some spinning to see where the center of gravity is and adjust it just right. Again, document everything, make sure all the covers are gone, all the things are gone. We do a test where you have those big Hollywood lights shining at the solar panels, making sure the spacecraft is capable of running on its own power. And then the first stage arrives, first stage of the rocket, gets put into the integration and then boosters, and the second stage, that gets put on top. And then they do a test where they fuel everything up. So the first stage, the second stage, everything, make sure everything works except pressing the launch button. And then one thing you'll notice here is the spacecraft's not on top. Right? And this is something NASA has learned to do is, when you do this test with a lot of explosives and stuff, there's no need to put the spacecraft up there. But the spacecraft, in the meantime, is being integrated in the fairing, making sure everything is as clean as possible. We had one of the cleanest fairings requirements of all missions because, again, we're going to an asteroid. We're spending $1 billion to get a few grams of asteroid dirt. We don't want what we bring back to be Earth dirt that we took with us all the way and back, right? So, again, we have these requirements to be super, super clean. And I think this is interesting from an optics standpoint because oftentimes we have to model how clean our optics are to look at light scattering properties and various other things. And so we go through this very rigorous calculation, assuming you have very clean optics. And then I'll show you a video from a launch, and you realize, well, even when you do go through all this effort, there's still dirt. So anyway, this is a picture of the spacecraft being hosted all the way up, put on top of the rocket. And then at the pad next to ours, so it's basically a mile away, there's a SpaceX rocket that's going through the same test where they fuel it up to make sure that everything is good. And but they hadn't learned yet not to put the spacecraft on top of the rocket when they did that. And that's the payload right there. So the interesting thing that happened is this is the pad right next to ours, right? And the the water and everything is going off, as you can imagine. And it's the same pumps that are shooting water to our pad or this pad, right? It's just in order to, during the launch, make sure that you reduce vibration and prevent stuff from burning. But now there's no valve or anything there left, so the water is just going and going and going. And you know, if the water from the tower gets depleted and the pumps are still running, you're going to run the pumps dry and they're going to be bust. And it's going to take weeks and weeks to replace them. And this is a couple of weeks before we're supposed to launch. And we have a very limited time window to go to this asteroid. So somebody has to run and turn the water off. But then they turn the water off, and when they do that, they realize that our spacecraft's got its own hydrazine in it. And hydrazine is a monopropellant. It turns on its own when you heat it up to 120 Fahrenheit. 120 Fahrenheit is not that hot in Florida. And guess what? The water system is what's keeping it cold. So now they have, okay, well, we can turn the water system, protect the pump, or we can turn the water system back on to protect the spacecraft. So they have to go through this whole trade in, you know, a few minutes to decide what they had to do in order to protect us. And they did an amazing job, right? So then just a few weeks later, we were able to pull out right on schedule and go to the pad. I'm going to skip through this because I'm already running out of time here, I think. So this is the night before. One of the things which I thought was really a good thing about this picture is you can see optics going on right here. There's a lamp right there shining on the rocket, and you can see the rocket faring up there on the cloud. So I thought that was cool. So this is just a quick video of the launch. So again, the nice thing about this rocket is they had all the cameras and everything on the rocket. So once it got out of view, you could actually still follow it and see everything that was going on, pretty much in real time, which I think is kind of nice to be able to have those little cell phone cameras. Is probably what they are, but where you're actually able to see what's going on. So, like for example, this camera where you can see the solid rocket booster being jettisoned in just a few seconds. You can see the next stage. So this is seen from the second stage now. And then the fairing opens, and you can see all the dust that's coming on from this, you know, very clean fairing still. And then the next video shows the spacecraft being launched from the second stage. And I don't know how much you can see, but you can see there's a lot of dust and stuff flying around. In my estimate, they're about 100 microns, just based on how bright they are. I mean, obviously they're not resolved, but based on how bright they are. Anyway, so then we start looking at all the cameras, making sure they're all okay. And this is the first picture that came from the camera that looks at the sample return capsule. And I mean, that's, you know, everything looks pretty. This is the radiator of the SAMCAM. This is what helps keep our detector cool. There's a really fun thing about this. This should have actually been in the dark, so we were pretty surprised that it was not. And then the sun is actually this way, and the shadows this way. So that was, you know, that was interesting. So it turns out that in the orientation we were at, there's a little opening between some baffles where the sun shines right through, hits one of the telescopes. From that telescope, goes back to another place, and then it was this kind of this ping-pong game to try and understand what happened here. But on the way out last spring, we got to do a little science. There's a region around Earth, 60 degrees ahead and 60 degrees behind in Earth orbits, in the Earth's orbit, where there's asteroids that are supposed to be, or at least thought to be. They've never been really observed because from Earth it's a very bad geometry, because in order to look at them, that means you have the sun setting or the sun close by, so it makes it pretty hard to look at that region of the sky. But we actually flew right through it, so we took advantage of going through to do a survey to look for them. We didn't find any. We did find 16 asteroids that were, turns out, already known. I mean, they were not known to us, obviously, but it was good to see that we were able to do this. But we were able to improve the science by reducing the upper limit for the population that exists there. And then it was also a good rehearsal because when we get to the asteroid, we want to be able to use our cameras to look if the asteroid has any moons or any satellites. And so by looking for bodies that are, in the sky but not known, that gave us an idea of what our actual capability is, which turns out is about an order of magnitude better than where we designed to. So we were pretty happy with the performance. And when we did that survey, the Jupiter just happened to be there, so we took a picture of it. And in September, we went by Earth and took a really pretty picture. I can tell you more about what happened at the top sometime if you're interested, but I don't think we have time right now. So what's neat? So this is a MapCam image taken from probably about what is it? Taken from probably the distance of the moon. And so you can see Baja California up there, and two suns behind clouds. There's Asia there, Australia there. But then if you use some of the filters and do some filter ratio, this is the vegetation index. And what shows up in green is that vegetation. And so some of the neat things, I think, is all of a sudden Hawaii stands out right in the middle of the Pacific. And then all of Polynesia and Micronesia sort of appear that you wouldn't see otherwise. And then you can also see Korea and Japan, which, in just the normal color image is a lot harder to see. But all of a sudden, you can see all this vegetation. So the neat thing is we're able to discover vegetation on Earth. We could use the spectrometer to also find that, well, lo and behold, there's carbon dioxide and water vapor in the atmosphere, that the average temperature of the ocean is about 13 degrees C, that the top of the stratosphere is about minus 40 degrees C. So we could pretend to be a spacecraft exploring a new world and get a sense of what we're capable of seeing. Something that's interesting and maybe sad is there was another spacecraft that did a similar flyby of Earth, Galileo, about 20 years ago, and had very similar instruments, at least in terms of spectrometers. And we're actually able to detect over this 20-year period an increase in CO2 and methane of about 15%. So just between these measurements of, this is not like an Earth observing platform dedicated for global warming or something like that. This is just using your typical instrument suite that you would use to go explore a new world. And then you compare the results from Galileo in the 90s and the results from our spacecraft now. And you're able to measure sort of 10-15% increase in those gases in the Earth's atmosphere. I mean, it's kind of, to me it was sort of like, wow. This is not like, we're not talking little changes. We're talking things that are easily measurable. And then this is a spectra from OSIRIS. And then I was going to stop with this picture, which is the last image we took with MapCam, which is basically Earth and the moon. And so in this picture, everybody who's ever lived on Earth, every human being that's ever been anywhere, including the astronauts that have been the farthest in the world. This is it. This is as far as we've ever gone. And so we're just looking back as we're sailing away from this little blue ball and then the moon just floating out there.